Log on, tune in, find out. Another good idea from Cambridge.
To introduce James Atkinson from Leeds University to talk about Schwarzian integrable systems and the Mobius group, a new connection.
Thank you, Rod, and I'd like to start by thanking the organisers of the programme and giving the opportunity to talk here. Yes, so I'd like to thank the organisers of the programme for giving the opportunity to talk here, and so I'm going to talk today about Schwarzian integrable systems. So to begin with, I'll give a bit of a background about that and where the term Schwarzian came into the theory of integrable systems. But what I want to talk is something a bit new. So there is a connection to a very simple object group of Mobius transformations. So to get there, I need to give a bit of, a few definitions, very simple definitions, to access the group of Mobius transformations, and then I can state a theorem which connects the two areas. And at the end, I shall discuss the impact this has on finding solutions, for example, of the lattice-Schwarzian KP equation and KdV equation. Okay, so to begin with, the lattice-Schwarzian KdV equation, which is written here, was first written down by. Okay, so first thing to say, I suppose, is this term in square brackets is why the equation has its name. It's the Schwarzian derivative. The term Schwarzian derivative was first coined by Cayley, which he named after Schwarz, but apparently it was discovered earlier by Lagrange in 1779. So that's where the term Schwarzian derivative comes from. But this equation, which is a PDE of KdV type, was discovered by John Weiss in 1982 when he was studying the normal KdV equation, and in particular its structure with regard to a generalization of the panel of a property to partial differential equations. And this, he termed this equation the equation for the singularity manifold for the KdV. And it's the same equation if you study the modified KdV with the same procedure. And Weiss gave Becklin transformations which connect this equation to the KdV and modified KdV. So it's equivalent to those equations up to Becklin. So one of the most important features of this equation is that it's Mobius invariant. So if you apply a Mobius transformation to the dependent variable u, then the equation doesn't change. So it's natural to think of the solutions of this equation rather than being complex valued functions of being functions valued in the extended complex plane, because the Mobius transformations can move the point of infinity to anywhere, so it's not a special point for this equation. But okay, so this equation is actually parameter subcase of an equation which was discovered earlier by Khrushchev and Novikov in 1979. But this parameter subcase was rediscovered by Weiss and noted to be Schwarzian in 1982. Okay, so the principle. So this is about discrete systems. But so this is all introduction at the moment. So the Becklin transformation I've written for the Schwarzian KdV is written here. This is a generalization of the one that Weiss knew, but this is the one which I shall be considering. So this is an equation between two variables u and u tilde, depending on x and t, and this is a semi-discrete, so this involves x derivatives and the two variables. This is also the same. It's x and t derivatives and the two variables, this other half of the Becklin. And it involves this parameter p, which will be crucial. So this is a free parameter of the transformation. So the story is that if you find the compatibility condition between the two variables in this equation, the Schwarzian KdV emerges as the compatibility constraint in each variable. So these Becklin transformations for different values of the parameter p commute in the sense that superposition principle or a permutability condition exists. So this is the permutability condition. So now what these things are. So I've introduced U and U tilde in this. U and U tilde are two solutions of the Schwarzian KdV. U and U hat are related by a similar transformation, but with the parameter P changed to parameter Q. And U tilde hat is the composition of two Becklin transformations. So I've written the equation in a bit of an unusual way. I've chosen to write the parameters, but that will become clear later when I want to make the connection to other things. That's the reason why I've done that. Okay, so a bit of history about this superposition principle. This was first written explicitly and termed the lattice Schwarzian KdV in 1995 by Nehoff and Capel. But actually it's a parameter subcase of a equation which they discovered previously with other authors, Nehoff, Crispo and Capel, in this paper. And that was 1983. So an interesting connection from integrability to another area, which is numerical analysis. This equation was written down by Wynne in 1961 as an algorithm for acceleration convergence. And this observation was pointed out to me by Vasilis Papageorgiou, who's here. But presumably Wynne didn't write it with a constant on the right-hand side in the form that I've chosen to write it. And these parameters P and Q will be important. They play a role in the integrability of this equation vis-a-vis the multidimensional consistency. So these equations parameterize these parameters parameterize this family of equations. So there's a two-parameter family here, and there's a commutativity or compatibility property between this family of equations, which is known as multidimensional consistency. This is the important property of the superposition principle. Okay, so on to KP things. This is a 2+1 dimensional equation written down again by Weiss in 1982 in the same paper. Again, it's invariant under Mobius transformation, and well, there is a Schwarzian derivative in there. It's known as the Schwarzian KP equation. And similarly, Weiss found transformations which linked this equation to standard KP. Discovered it as the singularity manifold for that equation. So to cut a long story short, here is the superposition principle for Becklin transformations for this equation. There's no parameters in this. So this equation is an equation now which relates 6 different solutions. If we have an original solution U, then U tilde, U hat, and U bar, which occur in this algebraic relation, are new solutions, and U tilde hat, hat bar, and bar tilde of the obvious compositions.
Notations. U tilde, U bar, U hat. What does it mean exactly?
So these are all at the moment. Let's say if this is the superposition principle for the solutions of Schwarzian KP, these are just solutions. So this is an algebraic relation between 6 solutions, and yeah.
Think about Becklin transformation.
Yeah. Importantly, there's a Becklin transformation that relates each pair of solutions. So U to U tilde, and U tilde to U hat, etc. So the equation in this form was written explicitly for the first time by Nehoff and Dorfman in 1991, and later it was found by Bogdanov and Konopochenko in 1998 when studying Becklin transformations for the Schwarzian KP. And actually, you can find it as a parameter subcase of the equation given in 1984, given by Nehoff, Capel, Weersamer, and Crispo, and the title of the paper is given there. And yeah, okay, so that's the main objects, the lattice Schwarzian KdV and KP equations. So the idea about them now being considered as discrete equations is that the tilde and hat shifts become increments in discrete variable. So we can form if you like, a lattice of solutions in 3 dimensions, in this case, of the Schwarzian KP equation using superposition. Or we can forget Schwarzian KP and just focus on solutions of the lattice equation itself. So there was an interesting development in this Schwarzian, discrete Schwarzian systems attributable to Konobuchenko and Schiff, who considered the discrete equations from the point of view of geometry, of planar geometry. And they wrote this paper with these two. So this is a connection to Menelaus theorem. Menelaus was a 1st or 2nd century Greek scholar who contributed by, and the connection there is that the Schwarzian KP equation relates theorems about intersections of circles in the complex plane, and the Schwarzian KP equation gives you the center of a circle which exists rather magically from a curve going through the points of intersection of other circles, and it also connects to a similar theorem of Clifford. Okay, so these are point circle configurations, but this is not connected to what I'm going to talk about. Okay, so that's the background. I've introduced the Schwarzian systems. And so I was studying solutions of these equations, but so this was an observation. So to make the observation that I want to tell you about, I want to first just define what I mean by Mobius transformations. So this is the normal thing, a set of transformations, non-singular invertible transformations, and they act naturally on the extended complex plane. So that's just the complex plane with the point of it at infinity added. And they form a group under composition. And I'm going to be interested in particular in the stabilizer subgroups of this group. So these are groups, subgroups of Mobius transformations depending on a point U. So U here is a point in the extended complex plane. It's the set of Mobius transformations which fix U. So it's very simple, clearly a subgroup, very simple subgroup. So this is the final definition, and I'll introduce it by example. It's not so straightforward to define it in the abstract. So this is a particular one of these subgroups. This is the affine transformations. So these ones fix the point at infinity, and I want to define. So for this group, I can define this alpha infinity, which is a homomorphism from S of infinity to the complex numbers under multiplication, and I just choose to send a Mobius transformation f to the value of a. So a is the value of this coefficient in this transformation. The fact that any group is conjugate to this one means that we can use this then to define alpha u. So this is the observation. S of u is conjugate to S of infinity, provided m sends u to infinity. So if we choose m in this way, then we can define alpha u, and it's a natural homomorphism from this group to the complex numbers under multiplication. Okay, so this is that concludes the definitions. So now for the observation, which is a very simple observation that connects the Mobius transformations to the lattice Schwarzian KdV equation. So given two Mobius transformations in this subgroup, they can be fixed by first of all giving the value of this parameter, this alpha homomorphism. So we take the value of the parameter for f to be p and for g to be q, so that we also give the other fixed point. So we know that u is a fixed point of f and g, and the other fixed point in this case is u tilde, and in this case it's u hat. So now u tilde and u hat are just playing the role of points in the extended complex plane. So I claim that this defines f and g uniquely, provided p and q are not equal to 1. but of course we can compose these. If we compose f and g, then it's another point in S. It's another transformation in S of u. So I'm going to compose them in this way, g to the minus 1 dot f. So this new transformation, g to the minus 1 composed with f, clearly has a fixed point u, and we can compute its parameter with this homomorphism alpha. It's just p over q using the fact it's a homomorphism. So to fix this new transformation uniquely, provided p is not equal to q, we need to find the other fixed point. So I'm going to denote this other fixed point as u tilde hat, and it should satisfy this equation. So you can see from this why I've chosen to this composition. It's more covariant with respect to this question. So I'm trying to answer this question: what is u tilde hat? And the observation is that this new point is determined exactly by this lattice Schwarzian KdV equation. Okay, so the observation as it stands is just an observation about a formula for composition with a particular parameterization of this group of Mobius transformations. But of course, we know the integrability property of this as a quadrilateral expression. When we treat it as a lattice equation, it's multidimensionally consistent, or more locally, it's consistent on a cube. So using this fact, we can then deduce some properties of Mobius transformations. So it's that I'll show you the consequences of the multidimensional consistency. Okay, so this is a theorem, and it will be useful to have a diagram of a cube. Okay, so I have here, let's say, that's a u tilde hat. So these are 7 points, which are the points I've got written in the theorem, points in the complex plane, and I'm going to associate them to the vertices of this as yet unfinished cube. And I'm going to assume that they're all distinct points in the complex plane. So this is a configuration of Mobius transformations I want to associate to these points. This doesn't fix f, g, and h uniquely, but f, g, and h all have fixed point u. The other fixed point of f is u tilde, the other fixed point of g is u hat, and the other fixed point of h is u bar. I'm free to do that. I've just chosen the fixed points of f, g, and h. It's not obvious that I can do the second line here. I can set the value of f and g and h and f to all coincide on these 3 other points. And in fact, yes, this imposes some condition on the points on this cube. And this condition is equivalent to the following condition. So now using the fact that we can define Mobius transformations uniquely by specifying their action on 3 points, 3 distinct points, I'm going to define Mobius transformations L, M, and N by their action on u hat, and u bar. So to view what's going on here, I'm defining of L that let's say L of u is u tilde. So L is associated to the vertical direction. So L of u, L maps u to u tilde, u bar to u bar tilde, and u hat to u tilde hat. Similarly, m and n are associated to the other directions in the lattice. So I'm just defining uniquely three Mobius transformations, and the so what I'm saying is that the condition on the points from the first existence of f, g, and h is equivalent to the commutativity of L, m, and n.
Sorry, James, what was the capital M again?
This is the group of Mobius transformations. This is the thing we're starting with. So L, m, and n don't live in S of u. They don't have fixed point u. They're three Mobius transformations which are just determined by these. We don't know what their fixed points are a priori. But we know that they commute if this is true. So it's also equivalent to the following, which is a far simpler statement. The previous two statements involved the point u in the bottom left-hand corner of the cube, and this one doesn't. So we know the condition doesn't depend on u, for example. So the Mobius transformation I defines, so I can define this Mobius transformation by its action on 3 points, and this is a bit different. So I is defined as the Mobius transformation which sends u bar to u tilde hat, u tilde to u bar hat, etc. So it goes across the corners. So that defines a Mobius transformation, and this condition ensures that that Mobius transformation is an involution, so its square is the identity. And this condition can then be shown to be equivalent to the Schwarzian KP. So it's just one condition, and this is the Schwarzian KP equation. Okay, so I can rewrite the Schwarzian KP equation in this way. This is maybe preferable from this point of view because there are many ways of writing this equation out, and the symmetry of the equation, which is obvious from the construction, is not obvious from this formula, but in this second formula it is. So this is a determinantal way of expressing the same thing. So this is a theorem about Mobius transformations. Okay, so it arrived because of we expected them to be the consistency on the cube of this configuration. So now where does that connect? Well, okay, hang on. I suppose, yeah.
Sorry, James, I'm just
Yeah.
trying to understand what is happening. So you get this discrete KP, the Schwarzian KP. You get that somehow from two-dimensional equations. Is that right? Or is that not?
Certainly it's a consequence of two-dimensional equations, but that's not, well, okay, so I guess I haven't made it very clear. So this theorem is, if you like, inspired by, but it doesn't follow directly from the previous observation. The previous observation was to do with the composition of Mobius transformations in S of u being connected to the Schwarzian KdV equation. And so the connection to Schwarzian KP is because when you try and prove that this configuration of Mobius transformations satisfies the property of multidimensional consistency, the thing that you end up trying to prove is the first statement. So do these Mobius transformations exist?
Well, put it another way. This discrete KP that you end up with, does that have some two-dimensional connection to something two-dimensional?
Right now, you're right. Then you take three Schwarzian KdVs,
Yeah.
three faces
Yeah.
with common vertex u. You eliminate u, you come up with Schwarzian KP.
Okay, so then my question is,
Yeah.
if you do something like that in 3 dimensions, would you end up with something integrable in 4 dimensions?
Well, no, that I'm not sure about. Certainly you can embed Schwarzian KP in 4 dimensions, and you can find equations which are a consequence of it, which live in 4 dimensions.
Before you leave this theorem, James, can I ask what the involution I does to you? Does it send you across?
Okay. So John, you're
Yes.
yeah. exactly.
Sorry, I meant
It's not there yet, but that's that's the next step.
Yeah,
So
sorry, I'll
yeah.
repeat it.
So the next thing will be the reduction back down to two-dimensional things, and it will involve exactly this. So okay, so this is the connection. This is the condition on these points for the existence of these Mobius transformations. Well, this is an intermediary step, and it's useful in proving the theorem. And it turns out that this also has a consequence when you look at the Schwarzian KdV equation. So I'll come back to that. Okay, so just for those who may be interested, if they know something about Mobius transformations, this is, if you like, stripping out from this theorem the equivalence of parts 1 and 2, comes down to some bookkeeping plus this lemma, which is slightly more technical maybe, but it's as follows. Let me state it. So we take four points. So I'll call them u tilde, u hat, and u tilde hat again. And we define just two Mobius transformations now. And in fact, this doesn't fix them uniquely. So we suppose that L and M have this action on those points, which is the same as before. We also suppose that F and G exist with fixed points u and u tilde, u and u hat, and they coincide on this other point, u tilde hat. Again, such F and G can always be found, but this doesn't fix them uniquely. So, and the statement of the lemma is that if L and M share their fixed points, then the composition of L with F and M with G share their fixed points. So this is a statement about Mobius transformations, but it can be converted to a statement, if you like, about two by two matrices by the natural association from matrices and Mobius transformations. So this is a statement about their invariant, and the fixed points then are associated to invariant subspaces of the matrices. Okay. So anyway, that's the technical detail about the theorem. So let me now move on. And the title of this slide is lattice Schwarzian Kp to lattice Schwarzian Kdv. So I'm now going to do this thing that John was suggesting, which is define a new point in terms of this Mobius involution I, and that's the action of I on U, and call it U tilde bar hat. So this thing is naturally associated to the final vertex of the cube. So this has an obvious meaning in the geometrical picture. So if we remember, this was the configuration of Mobius transformations that we had previously. This is the same. I've just copied it here. So I want to determine these more. I want to pin these down a bit more specifically. So I'm going to label the value of this abelian of this parameter from the homomorphism alpha to be P for F, Q for G, and R for H. So now F, which is defined as a Mobius transformation with fixed points U and U tilde and parameter P, fixes F uniquely, and similarly G and H are fixed uniquely by this. And these other points which are involved in this configuration satisfy this equation. This is what we observed previously, but this second one is a new observation. It involves the U bar tilde hat, this new point. So these are the same equation, but on two different faces of this cube. So one's on the front face and one's on the back face. And this equation can be deduced very easily from this one, because we just conjugate everything here with this involution I. And in so doing, we change all the tildes to under tildes, and this equation follows. So this is a sort of easy consequence then of the previous theorem. Of course, similar equations also hold on the other faces of the cube. So this is the natural embedding of the Schwarzian KdV equation into 3 dimensions. Okay, so what about the consequences of the second part of the theorem? So assuming that all the previous statements hold, then this one certainly does. And the interpretation of u bar tilde hat in this case is that it's exactly the action of these Mobius transformations on these points. So it's what we'd expect. If we apply the Mobius transformation on these three other points, we arrive at the same thing. An interesting thing about this observation is that if we suppose that the fixed points of okay, maybe this is not so obvious, but the commutativity of these Mobius transformations in this case is equivalent to them sharing fixed points. So they all have common fixed points. If I label those fixed points u0 and u1, and we can always write a quadratic equation which defines these points. If I write them as u0 and u1, then the following equations hold on the faces of the cube. So if we just concentrate on this equation in the lower left-hand corner, first of all, it involves these 4 points. And where does it come from? Well, if I have a Mobius transformation, let's say, so these things are just what are written above in the top left-hand corner. And this is just a statement that u0 and u1 are fixed points of L. Then that's an overdetermined system for the Mobius transformation L. And so there's some condition on that set of points. And that condition is exactly this equation. So as a result of this connection with these LMN Mobius transformations, we also have the interesting fact that these equations are satisfied on every face of the cube. So these involve 4 points, and these new parameters u0 and u1. Okay, so that's the observation. I think that when we and I guess this is where the work stops. In fact, this is the end of the talk, although it's a little bit early. But let me make the comment that if we want to embed these systems in three-dimensional lattice so that we have really dependence on discrete variables, then whereas the previous equations involve the same parameters on each opposite face of the cube, and we can deduce that these parameters must be continuous as we make increments in other directions in the lattice, and so we end up with an autonomous system. In this case, the system will be non-autonomous. So u0 and u1 associated to each cube in the three-dimensional lattice will generically be different on each cube. So this is a system of compatible non-autonomous equations, which define solutions of the Schwarzian KP equation, which are equivalent to the Schwarzian KdV reduction. Which is this one. Okay, so that's the end of the talk. Although I apologise for it being so short.
Is it possible, can I understand your result that simply this Schwarzian KP is just some statement about Mobius group, just relations, completely equivalent, and all theory of KP in principle can be extracted? This is relation.
Actually, I mean, well, okay, so the statement is that there is a configuration of Mobius transformations, and its existence is guaranteed by the points involved satisfying Schwarzian KP equation. I mean, maybe it's possible to deduce some integrability property of the Schwarzian KP equation from the Mobius transformations, some higher dimensional consistency. But what this is about really is the ideas go both ways. First of all, I've used the integrability property of Schwarzian KdV to tell us something about Mobius transformations, and that's the main step. The backward step then is to use the association with Mobius transformations to tell us something about solutions of Schwarzian KP. And yes, you can prove the integrability property of Schwarzian KdV from the Mobius transformations, but that's not the way I did it. So, I mean, it's not an obvious result about Mobius transformations. I'm not sure. Maybe it's well known in certain areas, but I haven't seen it before. So.
Yes. And this fractional linear transformation, Mobius transformation, is it some sort of byproduct of, say, association of this theory with linear operators or not? It's fractional linear might be obtained as a ratio, or yes, but just
Yeah. Like, well, I mean,
probably, yes. It was my impression.
yeah. I mean, the statements can be transferred into statements about invariant subspaces of two by two matrices. Yeah, but I have a generalization in mind where that's not so natural. So that's the reason why I've done it in this way.
What is the more precise connection between the parameters P and Q and the U0 and U1? Is there an easy connection between them? You know, you talk about this non-autonomous.
No, it depends on the data. It depends on the other, on U tilde, U hat. Depends on your solution. So, yes, this is something that's worth investigation, because essentially, if you could write that down, it would give you a transformation between the solutions of Schwarzian and the solutions of this non-autonomous system, because you need to transfer the constant into the equation. Yeah, but no, you can write down a relation between them, but you can't avoid it depending on the dependent variable.
I just want to comment, James, that I think it's quite serendipitous, because your determinantal formula that you've shown, it will appear in my talk in a different guise as some relation between abelian functions and things too. So I think I need to maybe try and understand how it comes about in yours.
There was no genus yet.
No, here there was no genus at all. Yes,
Yes,
so maybe I have some special example of this formula.
So you started with the Schwarzian KdV, which is the singular manifold equation coming from KdV. Can you start with another integral system?
So
Similar structure with Mobius transformation.
if you go back to the work of Weiss, and he did this for, I've shown it for potential KdV, modified KdV, and KP equations. So his work stopped after Boussinesq, Berger's equation, several others. There's a list which he tackled, and it's an interesting question, because the technique he applies can be in principle applied to other equations. I don't know whether or not it was applied and failed in some other circumstances, and there are some obvious other equations which exist where potentially you could construct a Mobius invariant Schwarzian type system from an old one. But yeah, this is not something which I've gone into much. In principle, but maybe there's a barrier. Maybe there's a problem. I'm not sure.
Any further questions? James again.